This is Logic and Computer Design Fundamentals. And in Chapter 2, we will talk about combinational logic circuits. It has two parts. In this part, we will investigate the gate circuits and Boolean equation. So in part 1, which is the gate circuits and Boolean equation, we will see binary logic and gates. We will move to Boolean algebra, and we will finish with the standard forms. In part 2, in another lecture, we will check circuits optimization with its subjects. The binary logic and gates, we have to define some terminologies first. Binary variables take on one of two values. The two values that we know is 0 and 1. And a variable, for example, x, could take the value 0 or 1. Logical operators operate on binary values and binary variables. Which means, for example, if you have two variables, x and y, one of the operators that you can perform on those two variables is the OR operator. Basic logic operators are the logic functions, and we have three basic operators: AND, OR, and NOT. The logic gates implement logic functions, and the Boolean algebra is a useful mathematical system that help us specify and transform logic function the way that makes it appear easier to understand and design and implement. We study Boolean algebra as a foundation for designing and analyzing digital systems. So if you want to design a complex digital system, you should know Boolean algebra first. Binary variables, as we said, they take on one or of the two binary values that we know. They have different names: true and false, on and off, yes or no, 1 and 0. And we use 1 and 0 to denote the two values usually. These are the values that we will see most of the times in our class. Variable identifier example. A good variable name could be A, B, or X, Y, Z, or X1, and they could be capital or small. We will start doing this in this class. Later, when you become good in design, you can name them an easy to understand name like reset, start it, add one, and things like this. The logic operation, there are three basic logical operations that we know, and you should understand them very clearly at the beginning of any logic design course. They are the AND operator, or AND operation, OR operation, and the NOT operation. We denote the AND operation by a dot, the OR by a plus sign, and we call it OR from now on, and the NOT by this sample, which we will call a bar. This is what we are going to use most of the time in this class. We can also use a quote mark or this mark before the variable, and they all denote the NOT operation. Sometimes they call this prime. So for example, if we have a variable x, we call it, if we want to get the negation of x, it's going to be x bar or x prime. It could be written also this way. Some of the notation examples, if you say y is equal to a ANDed with b, it reads, as we said, the y is equal to a and b. If you have this, then it reads z is equal to x or y, meaning this is not the multiplication that you used to know in the logic design in environment or in the logic design world. It is and this sample is or. This equation is read is x is equal to not a, or you could say x is equal to a bar. Note the statements. 1 plus 1 is equal to. This reads the way that I just mentioned to you, and this is what you know, I think, in the elementary school. Now, in our case, 1 or 1 is equal to 1. To understand this better, we will discuss the operator definitions. The operations are defined on values, 0s and 1 for each operator. Now, and if we say the AND operation, if you have 0 ANDed with 0, you could understand it as a statement 0 ANDed with another statement 0. If this statement is false and the other statement is false, then the result is also false. If it is 0 ANDed with 1, then the result is going to be 0. If it is 1 ANDed with 0, the result is going to be 0. If the result 1 ANDed with 1, and this is the only case in the AND operator where it equals to 1. If you want to try to understand it using the statements, then if you have two statements, the first statement is true, and the second statement is also true, then both of the statement together is true. Moving to the OR, 0 or 0 is equal to 0, 0 or 1 is equal to 1, 1 or 0 is equal to 1, and 1 or 1 is equal to 1. You can see here that as long as you have a 1 in one of the inputs, or both of them together, then the result is 1. The only case in the OR that has the result equal to 0 is if both of the variables are equal to 0. The NOT operator, which is the easiest operation, if you have an input, you just flip it. So 0 bar is equal to 1, 1 bar is equal to 0. To define the same thing in an organized way, we use truth table, which is a tabular listing of the values of a function for all possible combinations of values on its arguments. These are the three basic operators in the form of truth table. So if we say and you have two variables, x and y, the output z, which is equal to x and y, is going to be this way. And if you look at this output, and you look at the output that we just discussed earlier, they match. To fill the truth table in an easy way, you start with the least significant variable, and you start filling it by 0, 1, 0, and 1. And then you will go to the next variable, and you will say 0, 0, and 1, 1. After that, you apply the operation, which is AND. So 0 ANDed with 0 is 0, 0 ANDed with 1 is 0, 1 ANDed with 0 is 0, and 1 ANDed with 1 is 1. Similar idea for the OR and also for the NOT. Now, I should mention that if you have two variables, then the number of rows in the truth table is equal to 2 to the power of 2, which is 4. In a general way, if you have n number of inputs, then the number of rows in the truth table is going to be 2 to the power of n. The logic gates, as an introduction, more related to history, in earliest computers, the switches were opened and closed to generate the logic 0 and logic 1 by magnetic fields produced by energizing coils in relays. This is a picture of a relay. You can see there is a coil here, and based on the current, either you allow the current to move or not by touching those two metals. It's called relays. The switches in turn opened and closed the current path to represent 0 or 1. Later, vacuum tubes, as you can see it here in this picture, they open and close current path electronically, replacing the relay. You can see that the relay here is kind of having a mechanical movement, but here is completely electronic. But as you can see, they are kind of big. Today, transistors are used as electronic switches that open and close the current path. And this is one chip that represents one transistor. And you can have now billions of transistors in only one chip. There are two kinds of gates. We have the primitive gates, which are basically AND, OR, plus an optional inversion, which is the NOT. So the primitive gate is a gate that can be described using a single primitive operation. From those primitive gates, we can compose complex gates, a gate that requires more than one primitive operation type for its description. The logic gate samples and behavior. We studied so far the AND, OR, and the inversion, or the NOT. The sample for the AND is this sample. We have the two inputs here, X and Y, and it's generating the output X ANDed with Y. This is the OR sample, X and Y also the inputs, and it generates the output X or Y. And this is the sample for the NOT. The X here is the single input, and there is a single output, which is the X bar. You can see here that we can extend the AND and the OR to more than two inputs, 3 inputs or 4 inputs, and so on. But the negation or the inversion, it always have a single input. Now, the representation or the truth table for the AND, OR, and the inversion is as we discussed earlier. There is another way of representing the same thing using waveform timing diagram, which is depicted here in this picture. So if we have two input, X and Y, and we say that x is 0, 1, 0, 1, y is 0, 0, 1, 1, for example. These are the inputs. Then the AND is gonna be, if we have 0 and 0, then the result is gonna be 0. 1 ANDed with 0 is 0. 0 ANDed with 1 is 0. And 1 ANDed with 1 is 1. Similarly for the OR, 0 or 0 is gonna be 0. 1 or 0 is gonna be 1. 0 or 1 is gonna be 1. And 1 or 1, it will generate 1 in the output. You can see in the timing diagram that we have this time axis. It moves with time. So you start from here and you start getting the result as you go to the right side. If you want to get X bar, for example, you can get Y bar as a practice. X bar would be 0. So the negation or the inversion is 1. If it is 1, then it's going to be 0. If it is 0, it's going to be 1. If it's 1, it's going to be 0. I should mention that here for education purpose, I write down the zeros and ones in the timing diagram. In other timing diagram, you won't have these numbers. It's going to be only low and high. So for example, if you want to find the result at that time here, at this time, you would say, okay, X is low and the Y is high. So X or Y is going to be high. Now we will see the primitive logic gates and truth table. These are the primitive logic gates that we discussed. We discussed the NOT, and OR. Additional, we have a buffer, which is kind of the opposite of the operation of the NOT. So if X, the input X is 0, the output F is going to be equal to X. There is no change. If X is 0, the output is 0. If the X is 1, then the output is 1. You might ask, then what's the purpose of having a buffer? Sometimes you use a buffer for organizing your design, and there are other advantages beyond this, the scope of this class. NAND is the opposite operation of the AND. And you can see in the sample, if we have the sample, then the NAND, you are adding only a bubble indicating there is an inversion after you calculate the AND operation. You do the inversion to get the positive or the opposite operation. So this bubble indicates an inversion after the AND here. So this AND plus this inversion, it becomes a NAND. Similarly here, if you see the NOT, you have a bubble here. We take out the bubble, so it becomes a simple buffer. Now we know the truth table of the AND. For the NAND, it's the complete opposite. You can compare this and this one, and you'll see that it's the opposite. If the output here is 0, then the output here is 1. Here is 0, and then it's 1. 0, here's 1, and 1, then here it's 0. You can think about the NAND by itself by saying the only case when it generates 0 if both of the inputs are 1. Other than that, it's going to generate 1. Now, to write the function for the NAND, the function is X ANDed with Y, all bar, indicating the complement of the resulting AND. So you say X ANDed with Y, all bar. This is the function of the NAND. We know the OR, truth table, its sample and its function. The NOR is the opposite. You can compare this output with this output. You can also say that the only case that is going to generate 1 is when the input, when the inputs is 0 and 0. If both inputs are 0, then it will generate 1. Other than that, it will generate a 0. Similar case, you can notice that there is a bubble here, indicating that the NOR operation is the OR, and after that you have a negation or an inversion. The function is X or Y all power. Now, we extend this to 3 inputs. This is a 3-input NAND and 3-input OR, 3-input NAND, and 3-input NOR. Now, since we have 3 inputs, then the number of rows is 2 to the power of 3, which is equal to 8. So we have 8 OR, because we have 3 inputs, X, Y, and Z. Now, you can see that the AND function will result in 1 only when all the inputs are equal to 1. Other than that, it's going to be 0. For the OR, it will have 0 in the output when all the inputs are 0. Other than that, it's going to generate 1 in the output. And this is going to be the sample. The difference between a 2-input and 3-input is the existence of the third input here, Z. Similarly for the OR. This is also the function. We have X and Y and Z. Here we have X or Y or Z. Now, if we try to find the, also before I move to the NAND and NOR, there is a misconception here that the AND operation is the opposite of the OR operation, and this is not true. You can see or check the output here and here. They are not the opposite. They are not the opposite. In this case, for example, it will generate 0, and also here is going to be 0. Here it's generate 1, and also here it's generating 1. So it's not the opposite. The opposite of a 3-input AND is the 3-input NAND. And you can see, if you compare this output to this output, that it is really a complement of the AND. And this is why in the sample we have a bubble at the end. There is another way of saying the same thing. Either you say that this is a 3-input NAND or an inverted OR. This is an inverted OR. If you check the truth table of the NAND or the NOR, you will find a similar result in the output. So the function of the NAND is X ANDed with Y ANDed with Z all bar. And you can see here that we omit the AND sample. It's okay to omit the AND sample. The 3-input OR gate, you can have 3-input NOR gate, which is an inverted AND, by taking the opposite of the OR. This is the OR function. To give the NOR, this is the NOR as a 3-input. And you can see that you have X, Y, and Z here, and this is the sample of the NOR function. You can also have similar truth table of the inverted AND. To convince you, I will take this as an example. If we generate X bar, Y bar and z bar, and we try to write them here in the table. So let's say we will try to get x bar, y bar, and z bar. This will be 1, 1, 1, 1, 0, 0, 0, 0. Cannot write the 0 here. So here also the y bar is 1, 1, 0, 0, 1, 1, 0, and 0. The z bar is 1, 0, 1, 0, 1, 0, 1, and 0 at the end. Now, after we generated x bar, y bar, and z bar, you will do the OR operation. So the OR operation of the red values, 1 or 1 or 1, is going to be 1. It's also going to be 1. As long as you have 1 in the red value, the result is going to be 1. The only value that has a 0 at the output is when the x bar is 0, the y bar is 0, and the z bar is also 0. The result will be 0. So it generated the same output as a 3-input NAND, which means you can understand it quickly this way. If you have NAND of 3 variables, it's the same as ORing their inverted version. So NORing 3 values, NORing 3 values is like ANDing their inverted inputs. We will study soon the Boolean algebra, and you can see that this function here is x bar, y bar, z bar. And we just proved that this equation and this equation are equivalent. Similarly here, the function is x bar, y bar, z bar. And we also can prove that they are both equivalent. Now, moving to the truth table and function for XOR and XNOR. XOR and XNOR, it could be 2 inputs or more. The XOR, which means an exclusive OR, so it's very close to the OR. If you compare the XOR to the OR, this OR, you will find in the OR it's 0, 1, 1, 1. In the XOR, it's 0, 1, 1, 0. So it's strictly having a 1 in the output if only one of the inputs is 1. If both of them is 1, it's going to be generating a 0 at the output, and this is the main difference between the XOR and the OR. The function of the XOR is you can look at it or generate the function by looking at the ones on the truth table. So this is the when the function is equal to 1, and this happens when x is 0, meaning it's x bar, and the y is 1, which means it's y. That's the first case. Or the other case, which is when the x is equal to 1 and the y is equal to 0. So that's the function of the XOR. And it could be written like this. F is equal to x, XOR y. This is the XOR symbol. This is the XOR operator. And this is the XOR symbol. The XOR symbol is very close to the OR with the addition of this curve. The XNOR is the opposite of the XOR. We can also say that when X and Y are equal, the result is going to be 1. And when they differ, the result is going to be 0. And then in the similar way, we can say it in the XOR, when the results are equal, or when the inputs are equal, here and here, the output is 0. And when they differ, the output is 1. The sample of the XNOR is similar to the XOR with the addition of the negation at the end. You can look at the ones here, and you have two cases, either X bar ANDed with Y bar, or X ANDed with Y. Another way for writing the XNOR is X XOR Y all bar, which is the XNOR. Now, if we extend the XOR to 3 input, you will have this truth table. So you can generate this table by finding X or Y. So you know that the result of X or Y, let me write it here, X or Y. If you generate those, 0 XOR with 0 is 0. Here it's also 0. Here it's 1 and 1. Here it's 1 and 1. And here it's 0 and 0. After you find this, X or Y, you will also XOR it with Z. So you'll get the red result, XOR with 0, it's going to be 0. 0 XOR with 1, they differ, so it's 1. 1 XOR with 0, they differ, so it's 1. 1 XOR with 1, they match, so it's 0. 1 XOR with 0, it's 1. 1 XOR with 1 is 0. 0 XOR with 0, they match, so it's 0. And 0 XOR with 1, they differ, so the result is 1. This is the way you fill in a 3-input XOR truth table. You could do the same for any multiple input XOR. This is the function of the XOR. You can also write it as 2 XORs by XORing, for example, Y and Z, and then the result, you XOR it with X. The function, you can find it also by trying to find the ones. So you have 4 terms. The first term is X bar, Y bar, Z. X bar, Y bar, and Z. And you can find the second, third, and fourth terms as you see in the slide. The 3-input XNOR is the opposite of the 3-input XOR if you compare here, and you can generate it in a similar way as we did in the XOR function. This is the 3-input XNOR. This is its function, X, XOR Y, XOR Z, all bar. And you can see that if you want to get the function by finding the ones in the output, for example, let's take the last one. It's gonna be X, Y, Z bar. X, Y, Z bar. So you will have 4 terms ORed together, as you can see here. We mentioned that you could design a 3-input XOR by having 2 versions of a 2-input XORs. 2-input XOR, you get the result, and then you do the 2-input XOR again to get the final result. There is a misconception that you could do exactly the same in the XNOR. So you'll have an XNOR and then another XNOR. This is incorrect. You should have a 3-input XOR, and once you're done, you do the negation at the end. This is the truth table of many primitive and non-primitive gates with its symbols and function. Now we will discuss a complete logic or universal logic. Any logic can be designed by any logic, any design you have, whether it's simple or complex. It might have only few number of gates, less than 10, or maybe hundreds or thousands of gates. They can be completely designed by using AND or and not primitive gates. This is why we call this group together universal or complete logic. Similarly, you can have a full design for any gate, whether it's primitive or complex, using only NAND. This makes the NAND complete logic or universal gate. Or you also could do it with NOR. Now I will prove those two to you, given that if you have and or and not, then you will have a complete universal logic. How can you prove that by having only an AND, you will also have a universal gate? To do this, we need to design the NOT, the AND, the OR, using only NAND. So to do the NOT, you can have a single NAND gate where it's both inputs connected together. In that case, you will have the output as X bar. To get the AND, you could have a single NAND followed by the inverter that we just had here. This will generate for you an AND function. You can notice here that we use only one NAND. Here we used two NANDs to generate it. For the OR, you could prove this by having a negation for the X, which means that I'm generating the X bar. Also the negation of the Y, which means that I'm generating the Y bar. And after this, you will NAND them together. To understand this, you need to prove that this equation is equal to this equation. We know that this is the OR that we want. And here, by this design, we are trying to prove that X bar ANDed with Y bar, all bar is equal to X or Y. To prove this, I can prove this to you using truth table. We know that truth table for this one is if you have X and Y, 0, 1, 0, 1, 0, 0, 1, 1, the OR function is 0, 1, 1, 1. So this is the OR function. So I did this here. Now I'll try to do this. To do this, I'll have X and Y again. 0, 1, 0, 1, 0, 0, 1, 1. And then I will generate the X bar and the Y bar. The X bar is 1, 1, 0, 0, the opposite of this. The Y bar is the opposite of this, which is 1, 0, 1, 0. And then after that, I will get their AND together. So I will get the ANDing of X bar ANDed with Y bar. To get this, it's going to be the AND function. And you can see that this is going to be 1. This will be 0. This one will be 0. And this one will be 0. After that, you do a full bar for X bar, Y bar, and this is going to be 0, 1, 1, 1, which is the opposite of this one. And you can see from this and this that they are equal. They are really equal to each other. So, in short, we represent the inverter by a single NAND. We represent the AND by 2 NANDs. And we represent the OR by 3 NANDs. And this way, we prove that if I can design any circuit using a NOT, AND, and OR, then for sure I can design the same thing by only using NAND. Because I can convert the NOT to NAND, convert the AND to 2 NANDs, convert the OR to 3 NANDs connected this way, and I will have the same logic. We can do a similar way for the NOR circuit or for the NOR gates to prove that it's universal. We can say the same thing for proving the NOR or the OR function and generating a 3 NAND circuit to make sure that any circuit designed by AND, OR, and NOT could be designed only by using NANDs if we have the following observation. We mentioned before, that this slide, that a 3-input NAND is similar to an inverted input OR. And similarly, a 3-input NOR is similar to the inverted input AND. We will take advantage of this, and we will say that if you have a 2-input AND, for example, then it's also could be represented by converting the AND to OR and inverted both the input and the output. Similarly here, for the OR, you will say that it's equivalent to an and you are inverting everything, the input and also the output. Now, since we here want to generate NANDs, you can see that there is a NAND already here. And this NAND is this one. And this bubble, or what we call the inversion, will be 2 inverters designed by the NAND that we have here. You can have the similar observation when you try to prove the NOR is universal and you convert the AND to only NORs. Now, we will try to show you like introduction to the lab by showing you how to do it in this slide. So there are integrated circuits, which are gates that are implemented in silicon chip. So for example, you could find this chip 7408. This 7408 is actually having 4 2-input AND circuits. And if you look here, you will see there is a shape here that looks like this. This indicates to you where is the first pin, because you can't see any numbers here. So this is bin number 1, 2, 3, and so on. And when you reach at the end, this is bin number 7. And on the opposite side, this is bin number 8. And then after that, you go down to 14. And this is what we have here. This is bin number 1, 2, 3, 4, 5, 6, and 7. So this shape should be here. And then after that, you have 8, 9, 10, 11, 12, 13, and then 14. To test those ANDs, what you do is first you make sure that you connect this ground to ground, and this is to a VDD source or a VCC source. And then you will have two inputs here. Those inputs usually is connected to switches where you can make them as 0 or 1. You can see the switches here. And then you get the result, the output result, and you connect it to a LED, indicating the result. If both inputs, for example, are 1, then the LED will light up. Other than that, because this is an AND, the LED won't light up. To see this connection for the 7408, this is a model. You will say that, okay, this is 7408. And you will connect this, the purple line, to a VDD source. So the VDD source should be connected here. This is the VDD. And it's connected to all these dots. So you notice that we have a VDD and we connect it here. And here we have also a ground in the above pins. And we connect the ground to this pin, which is this pin. After that, I'm trying to test this one here. So I will connect both of 1 and 2 to switches. This is to a switch, and this is to another switch. And you will get the result, which is here, and you connect it to a LED. Now, to generate 0 and 1 in the switches, you should connect one of the pins of the switch to VDD, and the other one, you connect it to ground, but instead of connecting it directly to ground, you have to use some sort of resistance. Otherwise, you might burn the circuit. So the resistor's job here is to limit the current, so it doesn't go to infinity. Similarly, you connect one of the pins to the other switch to VDD, and the other one, you connect it to the ground, but with resistor in series. After that, you connect that to the pin number 2. And to test the AND gate, you get the result in 3, and then you connect it to this LED. You can see there in the LED, you have 2 pins. One of the pins we connected to the ground, and the other pin we connected to this output. Connected to this output. I should mention that here all this column is connected together here. So this one you connect it here, and after that you have this connection to the LED, and this goes to the ground. VCC or VDD in the other one. This is a real connection, as you can see. This is a real connection to test one of the circuits. You have other chips. For example, this one, 7432. It has 4 ORs. And 7404, it has 6 buffer or inverters. It depends on the circuit. Right now, I can see buffers. And you have another circuit for also the inverter. This is the connection. You can see that we got the source, the VDD and the ground from a battery. And we connect one of the pins to the VDD source or the VCC source, and the other we connect it to one of the terminals of the switches. The ground is connected to the other terminals. It's good to have resistance here, also here, and also in the output, either here or here. You put resistors to limit the current. and there's this 0 connected here, and you can test, for example, the NAND that was here. The inputs are in 1 and 2, and the output is in 3. So right now, since this is connected to VDD, this switch is connected to VDD, and this switch is also connected to VDD, this LED is supposed to light up. And you can do the truth table of the NAND. You know the truth table. If we say that this is X and this is Y, this is the truth table, X and Y. 0, 1, 0, 1, 0, 0, 1, 1. And to confirm that the AND that was here works correctly, then you test all the input combination. The first one, you're supposed to get 0, and here you're supposed to get 0, and here you're supposed to get 0, and the last one you're supposed to get 1. And this switch setup, it's connected to VDD. The X is connected to VDD, meaning logic 1, and the Y is also connected to VDD, meaning logic 1. So the LED supposed to be on. It should light up. You can test the other combination. If you switch both of the switches to the other direction, then you are testing the first row, and you can do the other rows in a similar way. Notice that this is 7408, and we mentioned that the 7408 is the 4 NAND chip. Now after we see the primitive logic and we see some application of it, we want to enforce the logic diagrams and the expression, the Boolean equation, or a Boolean function, which in this form. Also the truth table and logic diagram. This is a logic diagram, and this is a truth table. They describe the same function. They describe the same thing. So let's see, you have a truth table, this truth table, and it's having this function being 0, 1, 0, 0, 1, 1, 1. We take this as an example. We can generate this function by observing the truth table. Also, we can do the same vice versa. By having a function, you could generate a truth table. So there is a one-to-one mapping. If you know the truth table, you could generate the function. If you know the function, you could generate the truth table. Similar thing between the truth table and the logic diagram, and between the logic diagram and the Boolean equation. So as we said here, truth table are unique, expression and logic diagram are not. This means the truth table, if you generate it for a certain function, it's unique, it's giving you the same thing. But the function, you could have many functions representing the same truth table. Similarly, you can have many logic diagrams that represent the same truth table. Starting from the Boolean equation, or this function, f is equal to x or y bar z, we can fill up the truth table by knowing that we have 3 variables at the beginning, x, y, and z. So we say, okay, we have those variables, x, y, and z. And then we start to fill the table, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. You should also, I remind you again that if you have 3 inputs, then the number of rows in the truth table is 2 to the power of 3. which is equal to 8. And we have 8 rows in this truth table. After you fill the x, y, and z values, you can generate the function by observing the terms. The first term here is x, which means whenever the x is 1, you can see that the x is 1 here, the output is going to be 1, regardless of the other variables, because they are not shown in the term. Similarly, for the other term, when there is y bar and a z, meaning the y is equal to 0 and the z is 1. Here we have the y is equal to 0 and the z is equal to 1. The result is going to be 1. Notice that there is a duplication here, which is fine. After you fill up all the terms, the ones that represent them in the truth table, the other rows will have a 0. This is the way to fill up the truth table if you have a Boolean function. Also, if you have a Boolean function, you can easily have the logic diagram like this. You have x, this is the first input, or with another entity. This other entity represents this term, which is y bar. This is y. So after the inverter, it's going to be y bar. And ANDed with z, which means the y bar, I have to AND it with z using the AND gate. And after that, you connect it to the OR. So that the OR, this OR is representing this OR. The first term is x, and the second term is this one here. The Boolean algebra, you need to understand the Boolean algebra to help you generate logic function or logic equations and timing diagram, also the block diagram. If you know knowledge about you have certain knowledge about the Boolean algebra, you understand it very well. This makes your understanding of the logic diagram, optimization in the next class easier. So Boolean algebra, is an algebraic structure defined on a set of at least 2 elements together with 3 binary operator, the OR, the AND the bar. That satisfy Boolean algebra laws. We will define the Boolean algebra laws. We have multiple laws that we'll see them soon. If the meaning is unambiguous, we leave out the sample of the AND. And this is what we are going to do. If you have an AND, we can put the AND sample, which is the dot, or we can take it out. The Boolean operator precedence. We need to know the order of evaluation in a Boolean expression. So you first evaluate the parentheses. After that, you evaluate the not. After that, you evaluate the and the or. And as a consequence, the parentheses will appear around any or expression. So as an example, if you have A, B, or C, C or D, and it together, you could, if you didn't have parentheses and you have it like this, you will see from the logs of that function that this is a term, this is another term, and this is another term. To make sure that the ORing order is correct, and you wanted B or C first, you have to include the parentheses here or the other term. So right now you have 3 terms. The first one is A, the second term is B or C, and the third term is C or D bar, and they are ANDed together. the functions that I just wrote, which is a without the parenthesis, is different function. It's not f, it's maybe g. They are not equivalent. So if you have to be careful about the or, and you should include the parentheses if you want to have the terms as shown in this function. After agreeing to these order evaluations and the usage of the parentheses, we can show you the Boolean algebra laws. We have multiple laws. The first one is the identity law, meaning if you OR the x with 0, it's gonna give you x. If you AND the x with 1, it's gonna be giving you the same input x. The 0 and 1 law, and you can see that we exchanged the operations here. We changed the 0 and 1 here. So what happens now, if you OR anything with 1, the result will be 1. If you AND anything, x in this case, with 0, the result is going to be 0. The inverse or the complement law, if you have x or x bar, so if you OR x with its complement, the result is going to be 1. If you AND the x with its complement, the result is going to be 0. Before I continue with the other laws, it's also good to make use of the true and false representation of the values to understand them. So x or false is x. X ANDed with a true statement, then it's going to be x. For example, here, if x is ANDed with its complement, or a statement x is ANDed with its opposite statement, the result will be, of course, false. We have the idempotent law. X or x is equal to x. X and x is also equal to x. We have the involution law, which is if you have x and you double bar it, so you invert it twice, you will generate the original x. And then we have the three laws, the commutative, the associative, and the distributive laws. The commutative law, you can exchange x or y or x. You will have the same thing. Similarly for the AND. The associativity is if you have x or y or z, if you want to get the result of y or z and then OR them together with x, is the same thing as if you get the x or y first and then you OR it with z. Similarly for the AND. The distributive law, you can distribute the OR to the AND or the AND to the OR. This should be easier for you. If you have x ANDed with y or z, you can distribute the x like this. And you have x ANDed with y or x ANDed with z. You can do the same thing also with the OR. This is true in the logic design world. So x, you can distribute the OR into the AND this way. It will be x or y and x or z. The De Morgan law, or you could remember it by saying break the line and change the sign. So you have X or Y, all bar. You break this line and change everything below it. So the X will be X bar, the OR will be and the Y will be Y bar. Similarly for the AND, break the line and change the sign. This is the De Morgan law. The X will be X bar, the AND is going to be OR, and the Y is Y bar. This is the basic Boolean algebra laws. And we can prove any one of them by using truth table. I already have proving to you some cases in previous slides, and we will see many proof in the future slides. As an example for manipulating algebraic law, or the Boolean algebraic law, we have the exclusive OR the exclusive NOR. The two input XOR function means, as we mentioned, X or Y, but not both. Also, the two input XNOR function, also known as the equivalence function. If you remember, the truth table of the XNOR is going to be, if you have X and Y, 0, 1, 0, 1, 0, 0, 1, 1, the XNOR, if they are equivalent, they will be 1. If they are different, then it will be 0. This is why we call the XNOR the equivalence function. The XNOR equals 1 if and only if X is equal to Y, implying is X is equivalent to Y. Other than that, it's going to be 0. The XOR and XNOR gates are complex gates. They are not primitive, because you can generate their function by using AND, OR, and inverters. The three input XOR function or more is called an even function, or the modulo 2 sum function. The three input XNOR function or more is called an odd function. So the XOR is the even function, the XNOR is the odd function. Now the part that we are interested in here is applying the algebraic law. The XOR identity here, if you have X, XOR 0 is going to be X. If you have X, XOR 1 is going to be X bar. If you have X, XOR with itself, the result is going to be 0. If you have X, XOR with its opposite, the result is going to be 1, which is actually a direct implication of the truth table of the XOR. The truth table of the XOR, if you remember, this is the X and Y, 0, 1, 0, 1, 0, 0, 1, 1. And the XOR will be, if they match, it's going to be 0. If they differ, then they are 1. So if you can see, if the X, if you take X, and in this case, it's opposite, let's say that the Y here is equal to X bar. So if you take X and its opposite, 1, then the result is going to be 1. If you have X and 0, then the result is also going to be 1. And that's what we mentioned here. So we mention an algebraic, Boolean algebraic law now for the exclusive, or when the X and is XORed with its complement. It's going to be equal to 1. If they are the same here or here, then it's going to be 0. Also, the distributive law applies for the XOR. So let's try to apply some Boolean algebra to implement the XOR. We know that the simple implementation for the XOR, X XOR Y, is X bar Y or X Y bar. And we take this from finding the terms of each row that have the output equal to 1. And to draw the Boolean or the logic diagram, you will have X ANDed with Y bar. And here you will have X bar ANDed with Y. ANDed with Y. X Y bar is this term. I mean this term. This is X with Y bar. And here we have X bar Y, which is this term. So this term is here, and this one is here. And then you OR them together. Another implementation for the XOR is using NAND only. To have a NAND, you can introduce two bubbles here. Two bubbles here. If you introduce the two bubbles, this will be a NAND. And this one here is going to be a NAND. And the inverted input OR is actually a NAND. But if you look at the crisscross behavior of the inverters here, we take it out and we replace it by a single NAND. This might not be clear from the block diagram. So we use the Boolean algebra to prove this. So we know that this F is equal, we are trying to prove that F, which is equal to X or XOR with Y, is equal to this entity. This entity we generated from the block diagram. And you can see that this is X. And here we have X, Y, bar, or all bar. And here we have Y. Here we have X ANDed with X, Y, all bar because there is another NAND here. And this one we have X, we have the Y ANDed with X, Y bar, all bar. And then after that, we generated the F, which is going to be this entity here, which is this one. X, Y bar ANDed with Y, this entity here is that one. And this one is this one. So you have now the first entity ANDed with the second entity, all bar. This is the first entity. This is the second entity, all bar. So to prove using a Boolean algebra, either you start from X or Y and try to move to this result that we just get from the block diagram, or you start from this and you try to go to this one. I picked X or Y, and I know that this is X bar Y or X Y bar. What I did is I have a double bar. Double bar doesn't change the Boolean equation, and this is the law that we have here. Involution law. And after that, I break this one, not a full break, half break. So I break this one. I made a bar here and a bar here because I want to generate something like this. And then by breaking this, the OR will become AND. After that, I added, or I ORed with each term here, y ANDed with y bar. And here, x ANDed with x bar. Because I noticed here, I have x bar y. We have x bar y here, and we have x and y bar. I need to get y and another one inside the bar. So I need to generate this one here. And we have two x's here, so I need to include somehow the x. So to include the y here and the x here, trying to from this one to generate this, and from this one I want to try to generate this. To do this without changing the function, I can OR with 0. Also here, I can OR with 0. And I know that y ANDed with y bar is equal to 0. Also, x ANDed with x bar is equal to 0. And I know it from this law. X ANDed with x bar is equal to 0. So I took advantage of this, and I kind of generated the y here and the x also here. After this, I use the distributive law by trying to get the common factor here, the y. And inside I'll have x bar or y bar. And here I got the common factor x. And inside I have x bar or y bar. Now, after that, I applied De Morgan law. So what I did from here to here, I applied the distributive law. From here to here, I applied De Morgan law in this part here. So I know that this is equal to x ANDed with y all bar. And I know that this part is x ANDed with y all bar. And this is the same result that we had here. So Boolean algebra help us understand that this is also an AND implementation of the XOR. Since we introduced the exclusive OR and the exclusive NOR for you, we'll have another example to just make sure that you understand that. If you were asked to design a 4-input odd function, and that's it, that was the question. You should know that the odd function is the XNOR. And since you have 4 input, you would say, for example, W, X or Y, X or Y, X or Z, all bar. By having XOR and an all bar in the function, this will be an XNOR. So the question was asking for an odd function of a 4-input design using only 2 input, XOR and XNOR gates. So we know that by factoring, we apply factoring. We have the X, the W and X together, and we have Y and Z together. And we only introduced this parenthesis. And now I can have the XOR of these, W and X, XOR together, and the XOR of this one, which is Y and Z. And after this, I XORed with everything. I have this and this. Let's say this is 1 and this is 2. So this is 1 and this is 2. I XOR them together. And after that, I have all bar by introducing this inverter. So this will be an XNOR, and those will be XORs. One of the application of the XOR is the parity generators and checkers. So a parity bit is added to an n-bit code to produce an n+1 bit code. So you have an original code, which is an n-bit, and you add one more bit, which is the parity bit, which is the parity bit. So the parity generator circuit, usually it's between two entities. One of them will be the transmitter, and the other one will be the receiver. The parity generator circuit in the transmitter side, it generates a parity bit by using XOR for even parity or XNOR for odd parity. This example here, we used XOR, which means that we are applying even parity. So what happens, you will have a code word. In this example, we have 3 inputs, X, Y, and Z. To generate the parity for them, you get the XOR of X and Y, and you get the result. You XOR it also with Z to get the parity. As an example, if the word that you have is 0, 0, 1, then 0 XOR with 0 is going to be 0, and 0 XOR with 1 is going to be 1. So the parity here is 1. You got the P is equal to 1. And this is the parity generator circuit, the blue one. After that, what happens? The transmitter, after he generates this, he gets this message 001, which is this one, 001, and the generated parity, the parity, which is this one, and send it to the transmitter. Send it to the receiver. The parity checker circuit on the receiver side, check the code word with XOR for even parity. If you are applying even parity. In our case, we will use the even parity. Or if you apply XNOR, you can do that, and it would be using the odd parity. And then it generates the E signal for checking errors. What happens now is, on the receiver side, it takes the X, Y, Z, and also the parity as inputs. So it takes 0, 0, and 1, and this parity as 1 here. And it applies the XOR, as you can see here. 0 XOR with 0 is 0. 1 XOR with 1 is 0. Now, 0 XOR with 0 is 0. So E will be equal to 0, meaning that there is no errors. E is equal to 0. There are no errors. So it helps by detecting the single bit errors. Now let's suppose that for some reason the Y here, instead of 0, along the path between the transmitter and the receiver, it was flipped to 1 because of noise or any other factor. What happens now, the XOR here will generate, instead of this 0, it will generate a 1, and 0 XOR with 1 is going to be 1. And this indicates that there is an error, which is the change that happens in the 1. So as an application of the Boolean algebra, we check the XOR and the XNOR as even and odd functions. We see their some of their applications and how the Boolean algebra help us in understanding some of the concepts related to that. After that, we will move to the duality. The duality of an algebraic expression is obtained by interchanging the X, interchanging the OR and the and also interchanging the 0 and the 1s. This is the only change that you are changing. Any OR, you change it to and vice versa. Any 0, you change it to 1 and vice versa. But you don't change the bars. The bar stays the same. So the identities appear in dual pairs when there is only one identity. On a line, the identity is self-dual. So now if we want a self-dual function, or we want to check for self-duality, you check if there is only one identity on a line, on this line. To make it easier to understand, if the dual expression is equal to the original expression, then it is self-dual. And that's not the case usually. If you have a function, for example, f, which is a or c bar, ANDed with b or 0, and you want to get the duality, you can get the duality by changing the or to AND. This AND to or. This or to and the 0 to 1. But notice that we didn't change the c bar. The a stays the same. Also, the b stays the same. This is the duality. And here, you can apply simple Boolean algebra by, if you have anything ANDed with 1, it will give you the same thing. You can see that this function and this function, they are not equal. They are not equal. So, meaning that f is not self-dual. Let's check another function, this function. If you want to get the duality, the AND will be OR, the OR will be AND, the OR here will be AND the others will stay the same. You can simplify this or keep it the same, it's fine. And you can check that, or you can see that they are not equal. Now for this case here, in this H function, which is equal to A ANDed with B, or A ANDed with C, or B ANDed with C. If you want to get the duality, if you are asked to get the duality of the H, you will change the AND to OR, the OR to AND, the AND to OR, and OR to AND, and this AND to OR. Notice that this is a term. You have 3 terms, and you also generated 3 terms. Now, right now, you can't make sure if they are equal or not. To make sure of this, you should apply some Boolean algebra. Also, you can use the truth table. You can generate the truth table of this one, the truth table of this one, and you will find that the truth table are the same. Alternatively, you can use a Boolean algebra. To apply Boolean algebra law, what we did here is we distribute A to this 2 terms. So it's A ANDed with A, which is A ANDed with C, which is this one. And then we did the B. We did the B. A with B, and also B with C. This is ANDed with the other term, and you can do the same by distributing the B everywhere 4 times. So it will generate AB, ABC, AB, and also BC. Notice, for example, the last term here is B ANDed with BC, which is BC. If you say B ANDed with BC, it's the same as BC, because B ANDed with B is equivalent to a single B. Similarly, you do the same thing for the C, and you generate those 4 terms. After that, you will take any resemblance. If you have 2, the same thing. If the same thing, you will cross one of them. So you'll have AB, you have ABC, you will have AC, you'll take one of them. And you will have also BC, you'll take one of them here. And after applying the Boolean algebra, you will check that you can say that this AB is AB ANDed with 1. And we kept this the same. We kept this the same. We also kept this the same. Why we did that? We trying to move from this to the original one, which is this one. So you notice that you have AB here, okay. You also have AC, which is this one. You also have the BC, which is this one. But you have an additional term you want to take out. One way to take an additional term is to try to find something that resembles it in the other terms. And you can see here that you have an AB here and AB here. So what you did is you will have an AND with one, and then you will make this one OR C. Because now you can take a common factor, which is AB, and you have 1 OR C remaining in between the parentheses. 1 OR C is equal to 1. So this will be out, and you will end up with the same function that you have it in the original H. This means that H is self-dual because H is equal to its duality version. Now we will apply some proofing for some of the algebraic laws, starting from the De Morgan law. So we know that X or Y all bar is equal to, you break the line and change the sign, which is X bar and it with Y bar. So if we generate the truth table for this one, and also the truth table of this one, this is the truth table of that. You write down the X, the Y, and then you will get the OR function. After that, you will get the complement of the OR function, which is this one. The complement is the opposite. And then you will get the X and Y, you'll get their bar version, and after that you will add them together and you will get the same thing. You can notice that this one and this one here, they are the same. And this is the proof of the De Morgan theorem if you have two input. There is an extension of the De Morgan theorem. If you have multiple input, it's also correct. And you can apply the same rule. Break the line and change the signs everywhere. So all the ORs will be ANDs. All the X's, X1, X2, and up to Xn will be X1 bar, X2 bar, Xn bar, and so on. This is another example to prove that A or A ANDed with B is equal to A. If you were asked to prove this, either you will use the truth table, like what we did in the De Morgan law, and I will leave this to you, or you can use the Boolean algebra. We will use Boolean algebra to prove this entity. To do this, we will start writing the steps, and here we will try to write also the justification, or what kind of theorem that were applied on that step. So let's start by having A or A ANDed with B, which is this part. What we are going to do here is we will apply this rule, which is that if you have X ANDed with 1, it's going to be equal to X. That's one of the algebraic law. And by having this law, what we did is we introduced this part here. The A, we ANDed with 1. We didn't change it, but we will make use of the 1. What happens here? After that, we will apply the distributive law by taking A as a common factor. So we take the A from here, and we end up with 1 OR B. After that, we know that 1 OR B, by applying this theorem, if you have anything ORed with 1, is going to be 1. Now we have B OR with 1, it's going to be 1. And then after that, we apply the last rule. If you have x ANDed with 1, it will be x. And a ANDed with 1, it's going to be a. This way, we proved that really a or b is equal to a. This is actually one of the algebraic or Boolean algebraic laws. It's called the absorption theorem. The absorption theorem, if you want to remember it quickly, if you look at this and you see two terms, something ORed with the same thing ANDed with another letter, then you can take out this completely. So what happens is we absorb this into the A. We absorb it, we take it out, and it becomes only A. Our primary reason for doing proofs is to learn. Because you can say that if you were asked to prove this one, you can use truth table to prove it, and that would be enough. Sometimes you are asked to prove by using Boolean algebra. This is why you should learn this. And also it helps us by careful and efficient use of identities and theorems of Boolean algebra. Also how to choose the appropriate identity of or theorem to apply to make forward progress, irrespective of its application. So usually you use the theorem and you know where are you going. You start with this one. And what you want is to get the A at the end. So what happens is, okay, I had to include something here. You should think about it this way. I have to include something here to take it a common factor with this one to take the B out. If you start by having this intuitive, then you will break it down step by step to get the correct result. This is another example. It's called the consensus theorem. The consensus theorem. AB or A bar C or BC is equal to AB or AC or A bar C, which means that we take this out and we generated this. This is called the consensus theorem. To prove this, you notice that you need to take this out. So you add 1 ANDed with this one, and then you get the representation of the one, which is A or A bar. This is the Boolean algebraic law that we used. And after this, we use the distributive. You distribute the B, C here and here. This is what we have. After that, you use the commutative. The commutative, we use it only to reorder, to make things easier for us. Because after we generate this, what we want is this is closest to this one, and we make them close to each other, and this one close to this one, we made them close to each other. And this way, I know that I could include in this part ANDed with 1, and this one, it will be ANDed with 1. And this is the law that I used with the commutative again to reorganize. After that, I take a common factor here. It's going to be the AB, the common factor here. It's going to be A bar C. This will generate 1 or C, which will be taken out. This will generate 1 or B, which will be taken out to generate only this one. So you can see that intuitive at the beginning, we noticed that we need to take this out. And to take it out, we have to include something, expand it a little, and then it will diminish by applying other rules. Another proof, if you were asked X or Y all bar ANDed with Z, or X ANDed with Y bar, and you were asked to prove that it's equal to Y bar ANDed with X or Z. To prove this, we choose to start with one of the sides, either the left-hand side or the right-hand side. And then from that, we will try to generate the other side. So we started with the left-hand side as usual. So we started with this side. We applied the De Morgan law in this. It will be X bar ANDed with Y bar. So we applied De Morgan law on this side here, and then ANDed with Z. And we have OR X ANDed with Y bar. After that, what I did is I did some commutative flow to reorder. This is to show that we need to take Y bar as a common factor. You can skip this completely. But to reorder, you use the commutative flow. We make the Y bar at the beginning here. We take the Y bar common factor. It ends up with, well, the leftover is X bar Z or X. After that, we use the distributive flow. We distributed this part. The Y bar, we keep it. And we did the distribution of the AND into the OR. So we did the distribution this way. This to the X. So we have the distribution this way. The X will be with X bar. And also to the Z. We distribute the OR into the AND. So the X will be X bar. You will have at the first arrow here, X bar or X. This is the first. And the second, you will have Z or X. By doing this, we eliminated the X bar or X. It will be 1. And you will end up with only Z or X. After that, you will generate the left-hand side. So that's another example of the Boolean algebraic manipulation to prove if a function is an equivalent of another function. You can notice that at one time we proved the absorption row, which is this one. It has another version, and there are other theorem or Boolean algebraic laws that could help us in minimizing functions. But you have the absorption, and we prove one of them, this one. We also have the consensus, and we proved this one. There is another one for the OR. The terms here are ANDed together. Now the terms are OR together here. We have 3 more theorems: the minimization, simplification, and the De Morgan law. We know the De Morgan law, and we covered it before. The minimization, if we have it 2 terms like this, you can notice that you have one variable ANDed with another variable at its original and its complement version. If this happens, or you notice this, the result will be Y. This is called minimization. Also, the absorption, we mentioned that. Simplification, you simplify by having, if you have this, you would say that if you have X or with another term that has the complement of the same variable ANDed with another variable, then the result, you will take this out. It will be X or Y. This is called simplification. So we simplify it. Notice there is a difference between the absorption and simplification. The absorption, you have the same variable. Here you have the variable and its complement ANDed with another variable. So you took the complement out, and you end up with this. If you have the same one here ANDed with another variable, you take the whole thing out, and it will be This is the absorption. We observe this completely. The simplification, you simplify it by taking part of it. So we proved the absorption and the consensus. This is super easy to prove. The De Morgan law, we also prove it. We will try to prove the minimization, which is this one. It's actually fairly easy to prove. From this part here, if you start from this part, you can take the y as a common factor. You'll end up with x or x bar. And this will be 1, which means that it's going to be y. And this is how we've done the minimization. Now we will see how to evaluate Boolean functions. This is just a reminder of what we studied before. If you have 4 functions, f1, f2, f3, and f4, and you have this truth table, f1, if you have it by this way, you have x, y, and z bar. How to fill the truth table? You will check where is x is equal to 1, and y is equal to 1, and z is equal to 0, because it has a bar. And it will be this case only. X is 1, y 1, and z is 0. You will have 1 here, and the rest are 0. This is how you did the first function. The second function, which is this one here, you would say that, okay, I have this function. The function first term is x bar, y bar, z. This is x bar, y bar, and the z is 1. So I put 1 here. Similarly, for those 3 or 4 terms, you will have 4 ones. You can check them yourself. For F3, you will have 1, 2, 3, 4 terms. And those 4 terms correspond to those ones. I'll have one of them as an example. Let's say take this one. This one will be x bar y x y bar z, which is this one, x y bar z. F4, you have 1, 2, 3, 4 terms. So this corresponds to 4 ones. This is how we apply the truth table. I should mention that we can simplify F2 to make it like this. We also can simplify F3 to make it like this. Similarly, F4 to make it like this. This simplification, you could do it by applying Boolean algebra. Or you could prove that this is equal to this by using truth table. We will have another method in the future when we talk about optimization. Trying to find the simplest version of any function. As you can see here, there are many terms, and each term has many variables. While on the other hand, the equivalent equation has only 3 variables with 2 terms. So we could also make use of the Boolean algebra to do expression simplification. To simplify a function, it means if you have many letters or many what we call literals, we can reduce this to few number of letters. So let's have an example. This example, we have A, B, or A bar C, D, or A bar B, D, or A bar C, D, B, D bar, or A, B, C, D. So to do the simplification, or you're trying to reduce the number of letters, you have to look carefully here and try to find at the beginning if you have any common factors. You will notice that there is a common factor between this one and this one. This is why we use commutative and we make them close to each other. You will also have common factor between those two, and we make them close to each other, and we left this one alone. We took the common factor, which is the AB. We take the common factor here, which is the A bar See? So you end up with D or D bar. From this part, you can take also the A. Let me do this on the side. You can say that you have A, B, and you take a common factor, which is 1 or C. 1 or anything, you will take it out. So you'll end up only with AB. Similarly, in this side, you will end up only with A bar and it with C, and you are left over with this one. Now, from this, you try to find common factors to reduce the number of letters even more. And you can find that you have B here and here. We took it as a common factor, and we end up with A or A bar D or A bar C. And from this side, you can see that here we can apply the simplification because you have A or with A bar with another variable. So you can't cross this completely. We apply the simplification here. So it will be B ended with A or D or A bar C. And here we have 5 literals. 1, 2, 3, 4, 5 literals. Compared to, at the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It has 15 literals at the beginning, and now we reduce it to only 5 literals by applying Boolean algebra. Another use of or usage of the Boolean algebra is complementing a function. We can apply De Morgan law or De Morgan theorem. What I just to remember it, we have this saying: you break the line and change the sign. So we use De Morgan theorem to complement a function. You interchange the and or operator, and you complement each constant's value and return. So if you were asked, this is if complemented, it means that you apply De Morgan law. So the F bar is going to be, you change everything. The X bar is going to be X, the and will be or, the Y going to be Y bar, the Z bar, the and between them is going to be or, the Z bar is Z. And you have parentheses here. The or will be and. The X is going to be X bar, the and is going to be or, the Y bar is going to be Y, the and here is going to be or, and the Z bar is going to be Z. Another example is this one here. If you have G, as you can see here, the complement is the A bar is going to be A, the or is going to be and, the B is going to be B bar, the and between them is the or, the C is going to be C bar. Notice that we have parentheses here. If you didn't put the parentheses, then the function will be different. The whole thing was ANDed with D bar. So now the whole thing will be, the whole thing here will be ORed with D. Now this part here was ORed with E. It will be ANDed with E bar. Of course, you can break it down to make it simple or to make it readable, but it is not necessary since you were asked to get the complement only. This is another exercises. If you have F and you were asked to find F bar, you would say that the F bar, I'll take the whole thing and apply De Morgan law. And then I will break it. I'm doing this step by step. If I break this line and I have it as 2 bars here, the or will be and then I will break this one. It will be A bar or B bar. I will break this one. It will be C bar, and the and will be or. And this part here, I kept the bar on them, and then I break it again, E bar, and it with D bar. You could do it you can skip all these steps by applying what we said, breaking the line and change the sign. So the A will be A bar, the AND will be OR, the B will be B bar, the parenthesis here, the OR will be AND, the C will be C bar, the AND here will be OR, and the E will be E bar, the OR will be AND, and the D will be D bar. You can find the complement of G. This is G. You can find the complement of G bar, as you can see here. Try to practice this and make sure that's correct. After that, after we finish the first part of this class, we will move to the standard forms. So we will discuss what are the standard forms, the minterm, the max terms, some indexing, the sum of minterms, the product of max terms, some other representation, and how to do the conversion in the next video.